Welcome to this session. My name is Renee McCormick with the National Math Science Initiative, and you have come back for more kinetics. This is approximately the next 25-ish% of this particular unit, and it is on something called integrated rate law, but don't let the name scare you. It's just analyzing graphs. We're going to do a technique we call linearizing data, mainly because calculus is not a prerequisite for this course. So we're going to graph different combinations of data involving concentration, natural log of concentration, and reciprocal of concentration, or inverse of concentration if you prefer. And we're going to make graphs, and we're going to deal with our good buddy y equals mx plus b, and we're going to determine relationships from this. So I really kind of need you to go back in time to whenever it was that you took Algebra 1. Could have been 8th grade, could have been 7th grade, could have been 9th grade. Doesn't really matter when you took it. It matters that you took it. And we're going to rely a lot on those Algebra 1 skills. Things like ordered pairs, graphing, being able to understand that when we talk about graphs and we talk about this versus that if you're going to use that versus terminology, it's always y versus x. So this I keep saying technology. This terminology is actually your friend. So you always know that the thing in front of versus is on the y-axis and the thing after the word versus is on the x-axis. So with integrated rate law, we deal with a different data table. And I mentioned in the last couple of recordings that you really have to pay attention to the headings of how your data is presented to you, because we have been dealing with concentration rate data, and now we have time. So it will actually be a measure of seconds, minutes, hours. So just pay attention to the headings at the top. So when we want to know how long a reaction's got to proceed to reach a predetermined concentration of some reagent, we can construct these curves or derive an equation that relates concentration and time. So if a question ever asks you how long, that implies time. And that's when you're going to go into this part of the techniques. Set up your axes so that time is always on the x-axis. And I've mentioned in recordings before that any time you have time on the x-axis, you have entered the land of rate. I don't care what class you're in. Math class, physics class, biology class, any class, even economics. If you have time on the x-axis, then you are analyzing the rate of something. And if it is a linear analysis, then the slope of the line, of that straight line, is the rate. Couldn't get any easier than that. You've got to learn to appreciate slope in lots of different ways in this course. So we're going to always set it up so that time is on the x-axis, and then we're going to plot 3 different entities, and this is where the memory work comes in for you. We're going to plot the concentration, the natural log of the concentration, and the reciprocal of the concentration. So if you think about those in alphabetical order, concentration starts with a C, natural log with an N, and R with the reciprocal, and so that's alphabetical order. And when we actually graph these, we are determining whether this is 0 order, 1st order, or 2nd order. So 0, 1, 2, nice little pattern, alphabetical order, natural log, think about the N, not the L, and reciprocal concentration. Inverse isn't going to work for you. It's got to be reciprocal. So I never worry about whether the slopes are positive or negative because my calculator is going to tell me that anyway, so why waste that brain cell? But there is a neat little pattern if you are so inclined to just give up and memorize it, and it's going to be negative, negative, positive. And the only reason it flips to positive is that we turned everything upside down to begin with. Because we're talking about a reactant, a single reactant, and obviously as time goes by, that reactant's concentration is going to decrease if this reaction is happening at all. So this is going to be a heavy graphing calculator lesson. You can do this the old-fashioned way with graphing paper and plotting points and using a 2-point slope formula to calculate slope. Don't know why you'd want to, because that's awfully slow. It used to take me 3 class periods to teach this unit, and now it takes less than 1. So I'm a fan of the graphing calculator and make no apologies for it. It's time for everyone to embrace it. It's been around since 1991. The good news is I'm going to give you one heck of a cheat sheet. So if you don't have math classes and science classes that have immersed you in this technology, well, I'm going to do you a huge favor, because I'm telling you, when you get to college, there's no such thing as a graphing calculator class that you can take for credit. They just expect that you know how to do it when you walk in the door. And so you can think fondly of me once you arrive on a college campus and know how to do a few things. So we're going to be able to do a lot of stuff with this, but we have to embrace these basic patterns. I see no point in memorizing these equations, because what you've already memorized is y equals mx plus b. What you need to memorize is the concentration, natural log, and reciprocal of the concentration, because we can derive, if we do y equals mx plus b, we can derive all of these equations off of this little bit of memory work. So if I'm talking zero order, what did I graph? Concentration versus time. So the concentration of reactant A in moles per liter would be found by the slope, which is going to be my rate constant, times what we graphed on the x-axis, which is time. Oh, that's the thing I didn't say. It's up here, but I didn't say that. The better part of this is that the absolute value of the slope is equal to k. That saves you a lot of algebra. So no matter which one of these you're looking at, k is always positive. That's a baby k. It looks more like an h, huh? There we go, a baby k. So I know that this is kt plus whatever the concentration was at time 0, the original concentration, or the concentration at time 0. Then when you actually do this in your calculator, you'll notice that the slope is negative, and you can toss that negative sign on there. Same song, second verse. What did we graph on the middle graph? We graphed the natural log of A. So if you want to know what that is at any moment in time, that's also going to be equal to minus kt, because it has a negative slope. But my calculator would tell me that. I don't have to memorize it, but you can if you want to. Plus the natural log of the concentration at time 0. And then finally, for the reciprocal one, that's going to be 1 over A, or A to the minus 1 if you like that better. And that's going to equal kt, because it does have a positive slope. Again, the calculator would tell you that once you've analyzed the graphs and plotted the data and plotted it all 3 ways to determine which order it is, to see what the best fit line is. So plus ln of 1 over A 0, A naught, just like we had E naught and G naught. All right, so also recognize, again, I say that that absolute value of the slope is k, because a rate constant is never negative. So you know, we did this before. Right? That's the differential rate law. So here we're using graphical methods to figure out what that exponent is, whether it's a 0, a 1, or a 2, and be able to write the rate law and be able to connect all of this back. The only difference is the experimental design, when we use this format, chose to measure the rate of the reaction, whereas when we're using this graphical format, only time data was given, not rate data. So just a different technique, but it makes a nice little total package when you're done. And it will be a total package. Is that good news? We've got 2 different ways, and only 2 different ways to figure all this stuff out. All right, so that's all this is saying. That once we figure out what the order is on that particular reactant by doing this graphical analysis, then we can write the rate expression, or rate law, which is simply rate equals k times whatever your critter was that you were analyzing, to the order you determined from analyzing the graphs, which would be 0, 1, or 2, depending on what you graphed. So we're going to set up your calculator so that time is always in L1. And I'm telling you now, you're going to see problems that are going to give you data tables where it's not always the first column listed. So don't get in the habit of going, oh, well, I'm going to put the first thing that's listed into L1. No, I want you to think. Yes, I use the word think. I want you to think. So think about the fact that we're always going to put time in L1, so you may even want to rearrange your data table, or label the top of the data table is a good idea. Then we're going to use Ls 2, 3, and 4 to display the Y variables. So obviously we're going to put concentration in L2. So concentration is going to go in L2. And then we're going to batch transform that column and make the column give us the entirety of the natural logs of each and every one of those concentrations. And then we're going to batch transform again over in L4 and make them give us the reciprocal of L2. So we want to use this system to set up the data given in the following exercise, because you knew that my calculator was up. You knew something was coming, right? So here are the data points that we're going to put in. But let's do a little bit of housekeeping first. And I'm also going to tell you to just chill, because just under this box in your notes, you probably have already noticed, there's a whole bunch of graphing calculator directions, just in case you're not already good at it. I'm really hoping you're already good at it and you're going, what is that crazy woman doing? Doesn't she know that we already know this stuff? Well, I got to tell you, I'm in some schools where that's the case and some schools where that's not the case. So I'd rather be safe than sorry. So I give you this cheat sheet so that you can help yourself remember the steps. Furthermore, if you found this video, hopefully you found the graphing calculator video where I'm actually teaching you how to do all this stuff just for the sake of learning how to do it, not in the context of trying to learn kinetics at the same time. So we're going to do a little bit of housekeeping. And the first thing I'm going to do is clear all of my lists at one time. So I'm going to go second, plus, and the fourth item on this menu right here is clear all lists. So item 4. Or you can go dinky, dinky, dinky down to number 4 and then hit enter. I'm way too lazy for that. I just use the numbers and the letters that are on the side to tell me what they are. And you're not done until it says done. So make sure that you are not afraid to hit enter. Some students are enter-phobic and are terrified of the enter button. Go ahead and hit it. It should say done. All right, the other thing we need to make sure is that your diagnostics are on. Now, I am on the new operating system. If you don't know what that means, you need to go look at that video and you need to upgrade your calculator. The easier thing to do than look at the video, to tell you the God's honest truth, is go to your math teacher or your science teacher and say, hey, I want that new operating system on my TI 84 Plus. It does have to be an 84 Plus. So what I'm about to do only works on that brand of calculator. So let me rethink this. Let me show you how to do it on an 83 or an 84. And this method works on all of the 83s and 84s, but it's not as fast. So here we go. Second, and see how catalog is the word written above your 0 key? So if you choose 0, this is an alphabetical list of everything this blasted machine can do. Anytime you ever forget where a command is, this is your friend. Just go find it in the alphabetical list. Well, I'm looking for diagnostics on, which I'm way too lazy to scroll all the way down through all the A's, the B's, the C's. I'm just going to go alpha D, and the D resides right above this X to the minus 1 button. Just be sure you hit your alpha first, which evidently I didn't. There's my alpha. It's on the screen now. And then D. There we go. And again, it's alphabetical, so I'm still going to have to dinky dinky down with my arrow. There we go. Passed it. Diagnostics on. So I choose enter, and again, execute the command by choosing enter. So the first enter pastes the command, the second enter executes the command, and now my diagnostics are on. If you do have the new operating system, and how would one know? Second, plus, first thing on the menu is about, just hit enter. The new operating system is 2.53. If you have numbers lower than 2.53, you don't have the new one. But if you do have the new one, you can just go mode. Notice these arrows down. Always hang out on the left-hand side. I teach physics as well, so I've got my radian degree thing fixed on degrees because, boy, howdy. When I first started learning how to use these, I screwed up a whole class of kids on a test one time by clearing all their calculators and not reminding them to do that. It was very ugly. Now, I have the chance down here at the bottom of the screen to turn my diagnostics off or on. And so if it's blinking and you hit enter, that means you changed it. So I'm going to go back over here and make sure it stays on. And I move away from it just to be sure, because it needs to be highlighted. That's TI lingo. My lingo is dark. It needs to be dark. Okay, so now what's going to happen is when I run a linear regression to analyze whether or not this data is linear, then I'm going to actually be able to see an R value on my screen. So if you run a linear regression and ever see only A, B, and C on your screen, as I'll point out in just a minute, you're missing your R and you need to come turn your diagnostics on. That's the fix for that. So here we go. We're going to type in all of this data. Okay, I lied. You're going to type in all this data. So let's go stat and edit, and you should have clear lists. Occasionally, you've been a doofus and you have deleted a list by accident instead of clearing a list. Delete is not your friend when you reside up here on the top, the tippy top of these list headings. So if that is the case for you, then just come back to the stat button. Item 5 is set up the editor, and it will put your L1, 2, 3, 4, 5, 6 back. So go down there and grab item 5, run item 5 by hitting enter, and now everything should be hunky-dory. There we go. So, like I said, you're going to type all this in. So what are you going to do? You're going to put time in L1 and concentration L2. Tricky, tricky, tricky little problem, this. Sorry to keep coughing in your ear. I don't know what's wrong with my throat today. But tricky, tricky problem, this little problem, because it switched the columns on you. So you must have an original thought when you start looking at these data table headings. I've only been warning you about that for about 2.5 hours now. So we always want to put time in L1. So you start typing. Go ahead, start typing. I'm too lazy for that. I work this problem all the time, so I have saved this data as a group. I'm going to go get it. I go back to memory. I go up to group. And this is only because I've saved it. I'm going to ungroup the group I've saved. And I know it's down toward the bottom because it's called integrated one. Went past it. Dadgummit. That didn't work out very well. You're probably beating me. There we go. And I overwrite list 1. I overwrite list 2. And now when I hit my stat button, maybe I caught up with you. There we go. So double check your typing. You can pause me. You can double check your typing once you're done typing. You may have already been so fast that you beat me anyway. Okay, so I've got all my data in, and here's what we want to do. Let's recap. We're going to make 3 graphs. And they go in alphabetical order. Concentration, natural log of concentration, and reciprocal of concentration. All along that y-axis, and time is the easy part on the x-axis. We're going to run linear regressions on all 3 of these, which are going to be L1, 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 L2, L3, L4. So I'm going to run L1, L2, L1, L3, L1, L4. I'm going to show you some ways to do that fast if you don't already know them. And down, down, up are the slopes I expect to see, and whichever one comes out to be the best linear relationship. Oh, how does one know the best linear relationship? We have our good buddy R, the linear regression correlation coefficient. Now you know why they call it R. That's a mouthful. So we are in search of a R value that is closest to plus or minus 1.0. A perfect line is going to give you 1.0. And in the land of experimental data, that's fake data. But you can run, when you do the experiment that NIMSY has put out that goes with this unit, and you do something called crystal violet, you're going to get R values on the order of 0.98, 0.99 something, and maybe even 0.999 something. It runs really, really well, that experiment. So it's not outrageous that we get really good R values in the real world. All right, so onward. We have L1 and L2, so I've got this one check ready to set up. What I need is L3. So I go to the tippy top. If you want to transform a batch of information, a batch of data, you have to be in that command line at the very, very top of the heading. I say tippy top. So notice down here on my screen it says L3 equals, and what I want it to equal is the natural log of all the concentrations that reside where? They reside in L2. So second, and notice that L2 is in blue above your number 2. So there you go, ln of L2. Boom, enter. There they are. Isn't that wonderful? Yeah, back in the old days we crunched each and every one of those out by hand. And that's why it took 3 class periods to teach this stuff. So now I need the reciprocal of all of those concentrations. Remember that concentrations still reside in L2. So you're still looking there. And so now I'm just going to take everything in L2 and take the reciprocal of it. I love the reciprocal button. I don't think it gets enough props. So I know you could type in 1 divided by L2, whatever makes you happy. The reciprocal button brings me joy. So I choose to hit the reciprocal button. And there they are. And I'm pleased with that because I'm looking at a concentration of 0.1. I'm looking at a concentration of 0.1. And even on a bad day in my head, I can take 1/10 and flip it upside down to be 10 over 1, lovingly called 10. So I'm pleased that that column came out that way. I just like to give it a visual check. All right, so what they want us to do first is determine the rate law and calculate the value of K. Well, to do that, I know that I'm going to have rate equals K times the concentration of this stuff into 0.5. And so what I'm really in search of is what is that exponent. This is not table logic time. This is graph time. This right here is what makes this graph time. Get it? Time, get it? Graph time, time is the heading on this data table. So I got to run these linear regressions. I'm looking for the best R value. So I'm going to quit this screen. I'm going to clear my screen just because it's messy. And we're going to go to the stat button yet again, but we're done with editing. We don't want to sort ascending or descending or clear a list or set up the editor. We want to calculate. So come over here, and if they'd asked me, I'd have put linear regression at the top of this menu, but nobody asked me, so it's down here at item 4. So I choose item 4, which puts linreg on my screen, and I know you probably have done this in math class, and I'm indeed not trying to insult your intelligence, so feel free to fast forward at this very moment. But I'm really wanting you to follow this pattern if you don't know how to do this. I'm going to tell it always, where's my X, where's my Y, and please plop that puppy into Y1. Because I know that these problems are multi-stepped, and I know that I'm going to have to calculate a Y value when I know an X value, and vice versa. So if I just get in the habit of doing this, it's going to be a lot simpler for me on working AP problems. The ones in the back of your book may not require this because they're all single-stepped and a waste of time anyhow. That's what UT homework is for, to get that drill and skill and the singular ideas. When we start working real problems like this one and AP problems, you really need a little bit of an algorithm or a pattern to follow. So here we go. I'm going to say, would you please, Mr. Calculator, I guess mine's a miscalculator in pink, huh? Go get my X's out of L1, comma, which resides above your number 7, and get my Y's out of L2, and comma one more time. I'm kind of speak the calculator's lingo, give it a comma. Could you put it in Y1 for me? So old calculator way, we go vars, and then we go to Y variables because I seek Y1. For the love of God, do not go to parametric or polar. Stay in the land of function. And Y1's the first thing on the screen. Okay. You can rewind that if you didn't get it. Rewind it. In the new operating system, it's a lot simpler. Alpha, trace, really gets me the fourth function, that F4 key right there. It's just, that's what I'm getting. And the very first thing that pops up is Y1. I like that lots better. And I hit enter, and now we have run it. So we are trying to beat 0.94 as a linear regression. In other words, this is not so linear. And I'm not even graphing it. I could graph it and look at it, but why would you want to if you've got something as fast as this that can tell you if it's linear or not? I'll graph it when I have to, and when I figure out which combo is the correct one, if I'm going to answer any of the rest of these questions, I'm going to have to graph it and let it calculate with that equation. But right now, I'm happy to just realize this is probably not what I seek. It's probably not zero order, because this is a crappy R value. I can beat 0.94. I think about like playing poker with no face cards. 9s are high. So let's do this. Let's go second, enter, and that got my command that I just did back on the screen. If you missed that, that was second, and the enter button, which has entry written above it. And so I don't want L1, L2, I want L1, L3. So I'm just using my back key to get there and go second 3 and type over L2. Now I'm running the L1, L3. So I'm doing this analysis, this one right here, L1, L3, to see if natural log implying first order is going to be the best. So I choose to execute that command by hitting enter. Look at all those 9s. That's a thing of beauty. That's really good fake data. I have a feeling we have a winner, but I need to kill off the last option just to be sure. So second enter. Come back over and put L4 in the place of L3, just to be sure that we don't come out with 1. We're back to 0.94. Okay, so what have we determined? We have determined that this is first order. And you can put the 1, you can not put the 1, it doesn't matter. Here's the cool thing also. When you do this and you get the proper set of data back on your screen, and this ain't it, I need the data that is for that graph, for the L1, L3 graph. I'm looking at the L1, L4. So let me do this. Second enter, rolls it back once. Second enter, rolls it back again. That was my best fit. I'm confirming that by visually looking at that. Oh yeah, that's pretty. That's my best one. See how this is y equals ax plus b? I do not know why TI chose to use a instead of m, but they did. So a is equal to 0.00693, which I'm going to call 6.93 times 10 to the negative 1, 2, 3. And its units for first order are going to be, because again, it's first order. So I talked about this in the last video. If you want to do the units quickly, and I'm not real proud of this, but it works. If you want to do the units quickly, when it's first order overall, and you only have one reactant, so if it's exponents 1, it's first order overall, put one little finger up because it's first order, and now drop a finger down if you want to know the units on K, meaning there are no molarities in the denominator, so this is simply seconds to the minus 1. And how did I know seconds? It's right there in the table. You really got to pay attention to headings. So I have determined the rate law, and I've calculated the value of K. You'll get much faster at this as we work, I don't know, 4 or 5 more examples. So now this data that's sitting right here just got pasted into my y1 again when I ran that command. So hang on to that slope value and let's look at our y1. Does that look familiar? Absolutely. That's the right slope value. Well, I don't need anything in that y2, so I'm going to clear that out. Let's do the same. If you got anything else in your y's, clear them out. Make sure you have this linear regression in. Again, how did I get it? By running linreg L1, comma, L3, comma, Y1. That gave me, that plops that algebraic equation for that y equals mx plus b into my y1. All right, so now I need to graph this. So you need to turn something on. I have one on and I have two off, but dink with your stat plot, and I went second y equals to get to stat plot to get to the screen. So I'm going to go fix mine. I need L1, L3. Got to remember what you're doing. I need a scatter plot. No fair with the line connecting points. You're big kids, you don't get to use that anymore. And I want my x list always in this case to be L1, and my y list was L3, because that was the combo that worked best. This one right here. Why isn't it printing? There we go, that one right there. L1, L3. And then I'm a fan of Zoom 9. I know it could get you in trouble sometimes, but I'm a fan of Zoom 9. This happens in the new operating system sometimes, and I do not understand why. Zoom 9. Isn't that a thing of beauty? Of course it hits almost every point because its regression value was 0.99999 for crying out loud. But now I have that equation graphed. When I have that equation graphed, I can calculate with that equation. So let's go back to this question. What is the concentration? You ask yourself, is concentration a y value or an x value? Look back at my graph. Oh, first of all, I need Ln of concentration, and that's going to be a y value. So they're asking me for a y value. What is that? So what is y when I know at 600 seconds? That's an x value. So if I go second and trace to get to that calculate function, the very first thing on the menu, when I choose enter, says x equals. We know that x equals 600. So you put that in, you take a deep breath, you keep your fingers crossed, and you hope. Dang it, that happens when the value is outside the Zoom 9 function. Zoom 9 autofits, so what we're looking for is filling in a value that goes with 600. So it fit basically to 400, but don't panic. Never be a quitter. Always go to. So choose to go to the error. See, it's blinking there, and it's like, hey, doofus, you can't do 600. Your range stopped at 400. No problem. Zoom out. Looks like nothing happened because you haven't hit enter yet. So you go zoom, and the third command is out, and then hit enter. Ah, look at that. It ooched all the little points together. They're not spread out beautiful all across the screen anymore, so it ooched them up. Now we ought to be able to fit 600 on there somewhere. So let's try again. Second, trace, value, 600, and there we go. So the concentration is equal to negative 6.46. What? Concentration negative? In what universe? On what planet? That's not going to happen. Oh, remember what you're graphing. See, it's the natural log of that concentration. So that negative 6.46 equals Ln of the concentration that you seek for N2O5. So Now, I'm going to just confess right now that a child taught me this. I love it when you guys teach me. So if I ever come to your school and work with you on a Saturday or whatever, and you know tricks on the graphing calculator that I do not know, I appreciate some reciprocation here in the sharing of graphing calculator prowess, and you need to teach me some things. So I actually did not know that it stores these values as x and y. So I used to write down, like I just did, the negative 6.461426. I don't want to lose any of those digits because I'm supposed to keep it all in my calculator. And it was a real pain until one Saturday morning a child looked at me and said, "Miss, do you know it stores that as y?" I'm like, well, heck no, I didn't know it stores it as y, because why would I be doing all that work if I had known that? So if I want to take the inverse natural log, which is what I need, in other words, I need e to this number, to the negative 6.46 blah, 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 in order to get my concentration. So the concentration of N2O5 is equal to this e to the negative 6.46. So I can actually put an equal sign there instead of a therefore. All right, so all I'm going to do is go second natural log, and that's not going to work because I'm in this screen. So let me go second quit to get out of that screen. Second natural log puts my e to the up there, and now I go alpha and y because it's stored it as the y value, and I don't have to type all that mess out and risk mistyping it. And I go enter, and it equals 0.00156. I'm sticking with the number of digits that are in the table, 3 significant figures, and they didn't put it in scientific notation. So then notice that I wrote it back up in my table because that's just good form if you want to get a good grade. I'm seeing if it fits properly in the table. So 600 belongs over here where the time is. Does this make sense in the context of what's going on? Decreasing, 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 decreasing. Oh yes, it's decreasing. So that seems like a reasonable answer. So the concentration of N2O5 is 0.00156. It's equally correct to put the molar there, but it's okay to leave it because what does that imply? That implies molarity. So you're good to go either way. All right, now, for fun, again, recap, what is the concentration? That's what you graphed the natural log of on the y-axis. So you're asked, what is y when you know x equaled 600? So on your calculator, you're using the value off of this second calculate menu. I wish there was a way to have just one little button so that you could do it the other way around. Because here, we sort of know what y is. I'm sorry. Yeah, that's right. We sort of know what y is when we're looking for x. At what time is code for what's x? When we know, sort of, y. We just know that y would be the natural log of this number, 0.00150. So I want to know what x is when I know y. So here's the fastest way to do it. You're all about speed. You're a machine. So I come down to y2 and I make just a single graph of the natural log of the y value that I have. Why natural log? Because that was the set of axes that gave me the best linear regression. It's the most linear. It determined this was first order. Blah, 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 blah. Now hit graph, and you should see an intersection. If you do not, ever, you zoom out again. It can only calculate the intersection if you zoom out. So this is like reading a graph the old-fashioned way off of paper. I'm basically saying, I know that the concentration that they are wanting me to find the time for is 0.00150, but I'm graphed a natural log of it. So use your calculator, get the natural log of it. You'd read that down a manual axis over here. You would run your finger across, and you would get right there, and then you would drop down to the x-axis, and you'd read it the old-fashioned way. Well, this is going to do it for us. We go second trace, and item 5 on the menu is intersect. So they say, is this your first curve? Yes. Is this your second curve? Yes. I've only got 2 curves on the screen. And no, I don't have time to guess. Just hit enter again. Just keep hitting enter until the intersection pops up on your screen. So when the natural log of 0.00150 is negative 6.5022 whatever, then x, which is time, and it equals 606 seconds. So let's see if that makes sense in our table. 0.00150 would be under 0.00156 and a mere 6 seconds later. And it all makes sense. Peachy. We'll get faster. Okay, that was your first one. You did good. If at any point you got lost, remember, now's the time. Pause, rewind, regroup. All right, and it'll be kind of fun because my screen will be clean for you. All right, so if ever you panic or you forget, here's the entire cheat sheet of exactly what to do. However, I think this is in, oh, see that jot down business? Yeah, that was before I knew what happened. Stored as oh, jot down your R, never mind. That one's not stored. But when we get down to the other part, things are stored as X and Y. Okay, lots and lots and lots and lots of stuff. All right, I'm going to skip this half-life thing for just a minute. No, maybe not. I'll go ahead and do it. There's a special application of half-life, so I'm going to put this away for just a moment. Make this bigger. Center it. All right, so let's talk about half-life. Most of the half-lives that you're going to deal with are going to be first order, such as nuclear decays. And so we talk about it first. Zero order is no big deal. Zero order, remember, is just a graph of concentration versus time. And a straight line. So that's just a read the graph moment. Gets a little trickier when you're into the natural log of the concentration or the reciprocal of the concentration. So you need to start burning into your brain that first order follows the natural log of the concentration function. So this particular handout that you're looking at on this screen is not as good as the one that you printed off of the wiki page because Adobe didn't like my little 1/2 symbols on this section. So it took them all out and made them 2s on my T's. So I'm going to fix some things before we really get started. And that's going to be that this should read 1/2, T1/2, and this should read T1/2. And this should read T1/2, and this should read T1/2, and I think I got them all. 1, 2, 3, 4. Yep, got them all. Sorry about that, but it should be pretty on your page and not messy like on my page. So let's just think about the words half-life. You've known this definition for a while, probably, like I say, in the nuclear sense. Like, you've heard of carbon-14? Of course you have. That's radioactive carbon dating, and I don't mean like in a boy-girl kind of dating sense. I mean in a I'm trying to determine the age of this fossil kind of sense. What was the date, the approximate date that this fossil thing was alive back thousands and thousands, millions, however long ago. So half-life is defined simply as the time it takes for 1/2 of a reactant to disappear, whether it's nuclear decay or whether it's a reaction, an actual chemical reaction. All chemical reactions have half-lives because you start out with some reactants and when half of them are gone, boom, however long that took, that's the half-life. Do not overcomplicate the concept. So at this point, there's different relationships you may want to pull from. Whatever is left, right, whatever that value is, would be twice the original value, or I like this one the best personally, that whatever you got over AO equals 2. So the natural log function is what we deal with in first order. And so the concentration of A at any given time is equal to the original divided by 2, the ln of which, so there's half of it, the ln of which is equal to K times T times the 1/2. And the natural log of 2 then, because this would be a big old fat 1/2 here once you clean that up. And if you then take this would be the 1/2. And if you take the reciprocal of 1 over 1/2, then you get 2. That's where that 2 is coming from. So the ln of 2 actually equals the half-life. And the ln of 2 is 0.693. Don't believe me? ln 2. See? 0.693. That is on the formula sheet. This is on the formula sheet in the free response. Just know that it's there and there's no reason to memorize it unless you just want to. It's not a bad thing to know for multiple choice, but most of the multiple choice ones are easier than that. So let's deal with half-life. a certain first order reaction has a half-life of 20 minutes. So you just told me T1/2 equals 20 minutes. Calculate the rate constant for this reaction. Well, if T1/2 equals the natural log of 2, 0.693 precisely, over K, then K is equal to 0.693 over T1/2. Mr. Thomas, 9th grade, taught me switcheroo. If you have a single thing over here and you want what's on the bottom here, just switcheroo. Or you can do the 3 steps of algebra. It's up to you. And that is going to be equal to 0.693 divided by 20 minutes. And you come out with something that looks goofy when you actually express it in minutes, 3.47 times 10 to the minus 12 minutes. Most people would put that in seconds, but that's not how the book did that one. But I think it's equally correct to put that into seconds if you wish. So that would be times 60 seconds per minute, so just multiply by 60. And 2.08 seconds is probably more logical to report as an answer. Either way you do it, it's fine. And that doesn't need to be SEC, that just needs to be S. All right, so how much time, what am I solving for now? Time. How much time is required for this reaction to be 75% complete? Now let's talk for just a minute about number sense. Number sense is that stuff that your elementary school teachers and junior high teachers, middle school teachers tried really, really hard to teach you. A little bit of common number sense. So 75% complete means I'm down to 25% left. Duh. Right? So if the reaction has proceeded to 75%, don't I have 25% of my original sample? So let's think this through in a multiple choice format kind of way. This is faster than doing the actual algebra math. 100% first half-life. Going to become 50% by definition. Go through another half-life. What's you going to be then? 25% left. Remains. I'll use the word remains. Bingo. That's what they're asking me. That's 2 half-lives. If each half-life was 20 minutes, 40 minutes. I don't need rocket science to be able to do that. So that is a technique that you need to master. And so sometimes we're asked about fractions, sometimes we're asked about this or that. Don't lose your common number sense. Think of it in that way, and I promise you're going to solve the problems quite a bit faster. Big tip for multiple choice problems, because half-life problems abound in the multiple choice section of the AP exam. Meaning this unit exam that's coming up. Shh, don't tell anybody I told you. Okay. The rate constant for the first order transformation of cyclopropane to propene is 5.4 times 10 to the minus 2 per hour. That's a K. What then is the half-life of this reaction? So let's solve for that first. T1/2 equals 0.693 over K. So plug your K in. And we're going to come out in hours, right? Because a 1 over an hour in the denominator becomes an hour when you flip it up to the numerator. And so 5.4, you can put the O if it makes you happy. Second EE -2, don't forget the negative sign, that's lethal. I should have not started that way, but I love the reciprocal button, times 0.693. I suspect you typed 0.693 divided by 5.4 times 10 to the minus 2 because you're smarter than me. All right, but either way, we should agree on 12.8 hours to 3 sig figs. Yes, 3 sig figs. 1, 2, 3, 1, 2, 3, 1, 2, 3, 3 abound. So that is 12.8 hours. And then what fraction? See here, now they're asking me about fractions. So you start with 1.0, or you start with 100% if they're doing it in percents. Don't freak out either way. What fraction of the cyclopropane remains after 51.2 hours? You need to expect easy math, especially in the multiple choice portion and sometimes in the free response portion. I see a multiple here. You may not, but I do. And I'm thinking that's about 4 times, but let's double check. 51.2 divided by 12.8. Looky, looky, exactly 4 half-lives. So if we start with no fraction, which is 1.0, we go through 1, 2, 3, 4 half-lives. 1 half-life, 2 half-life, 3 half-life, 4. Then doesn't this become 0.5, 0.25, 0.125, think harder, 0.625, and we're there. So what fraction remains? I'll put the 0 in front as a placeholder for good form. There you go. That's the fraction that remains after 51.2 hours. Now, sometimes you don't get that lucky, like the next one, 18 hours, 12.8 hours of a half-life. I'm not seeing an easy fraction there. So what fraction remains after 18.0 hours? So now you got to do it the hard way, the longer way. It wasn't as easy. So you always want to try to see if you've got just an easy multiple of half-lives first. But when you don't, you got to give up and go to the longer way, which is, I'm going to do it in purple to differentiate it from the rest of this work because I didn't leave myself enough room here. ln of the fraction, A over AO. Remember that the original would be greater since this is a reactant. So I definitely write this as a fraction. To write it upside down would be an improper fraction. That ain't a fraction. Is equal to minus KT. So that was back up in the notes. So this is a handy little way to do this. And that is equal to E. Oh wait, that's equal to what? 18 hours. Okay, so let's plug that in. Minus 5.40 times 10 to the minus 2 per hour. That's my K. And what is the T? 18 hours. Clearly those are going to cancel. And I'm going to come out with ln of fraction that I seek is equal to negative 5.4 second E minus 2 divided by, times 18 hours. And we come out with a negative is very important, 0.972. Therefore, the fraction is equal to the inverse natural log of that. So second ln puts the E on my screen. So it's equal to E to the negative 0.972, which is equal to, go grab it. In the new operating system, you can just arrow up and grab it. Otherwise, you can type it in. Or you can go second answer and have it pasted in. Enter. 0.378. 0.378 is the fraction that remains. Okay, so that's important. And back to one that we're going to have to graph. All right, the following data were determined in the laboratory. So we've had our little half-life moment. We're getting back to what we have to really do, because this may ask me for half-life along the way and kind of tie all these concepts together. So we're going to be working on the calculator for a while now. So if you need to pause me, go get a beverage, come back, go take your shoes off, whatever you need to do to get comfortable. We're going to work our little fingers for a while. For the reaction with trimethyl, carbon, bromo, whatever that stuff is, with hydroxide, the following data were obtained in the laboratory. Plot these data as, it tells me to plot them as ln versus time. Well, that makes it easier. I don't have to do all three. So, to get started, second plus, item 4 is clear all lists, and hit enter. That's just faster than clearing them one at a time. Plus, you aren't risking deleting them by accident. What did I say earlier about where we put stuff? Time always goes where? L1. And in the concentration goes in L2. And then I'm going to take the natural log of the whole bloody mess of L2. 0, 30, 60, 90. 0.1. You can put the OOs, but it's just going to knock them back out. Also, if you have a whole bunch of digits, we don't have very many, so I'll display. If you get longer significant amounts of significant figures, it will round them. It keeps them exactly the way you type them, so don't panic. It just can't display them all, so it will round them into fit into those little vertical bars either side of L2 to cordon off its column. All right, so they tell me to plot it this way, but right now they're not natural logs. So dinky your way up to L2 at the top and go ln of L2. You don't have to create an L3 unless you just want to. But I got everything right there that I need. And sketch your graph. Okay, so that means I got to go plot L1, L2. Second y equals to get to stat plot. My current plot is L1, L3. That will never do. Second 2. Cool. Zoom 9. I hate it when it does that. Clear. Zoom 9. Isn't that beautiful? Why doesn't that fit? Because I haven't run the right linear regression. See, sometimes looking at the visual is helpful. So let's clear. Still got my stuff in from last time. I never ran the regression. So let's run the regression. Stat. Item, go to calc. Item 4. Second 1, comma, second 2. Yes, I know it defaults L1, L2, but I just stay with this pattern, and I think it's easier for you too as well. And now I got to get that Y1, whichever way you get it. Vars, Y vars, enter, or alpha, trace. There it is, thing of beauty. Choose enter. Now when I hit zoom 9, this little bloody thing, that's better. Okay, so sketch my graph. Pretty easy to sketch. All right, where you need to label these axes. These are time. Look at your data table. Go ahead, look at it in seconds. And this is ln of this critter. CH3 3 times CBR. There's my sketch. Is the reaction first order or second order? Well, that's a silly question because you told me to plot ln versus time. How could a person possibly know that? Unless I ran both regressions. So let's run both regressions. First of all, let's go back and fix our data to be able to do that. I didn't write this problem. I'm annoyed by that. Okay, so L2 has this. I need an L3 that's going to have the reciprocal. That doesn't look like parentheses. CH3 3 times CBR. All right, so let's go over here. First of all, I got to undo those natural logs. So this is going to take a little bit more creativity on my part. I go up here and I say, okay, give me the second natural log of everything in L2. That ought to get my data back. 0.1, 0.074. Oh, smarter than the average bear, huh? Now I just need the reciprocal of that. So x to the minus 1. Nope. Everything in L3. X to the minus 1. Enter. There we go. So now I need to graph L1, L3. Oh no, just run the regression. So second quit, stat, calc, 4, second 1, comma, second 3, comma. I know what you're thinking. Why didn't I just go back and grab it? I don't know. It didn't occur to me at the time. And now alpha trace. Thank you very much. Execute it. 0.99. So if I go back a few times and I go back and get the L2 was better, trust me. I don't want this equation pasted into my y equals anyway. So second 2. See, that was way better. The other one started off 0.99, this one's 0.9999. 2 of a kind, 4 of a kind. Who wins in poker? The 4 of a kind. This is the best fit. So is the reaction first order or second order? First order. Since the most linear graph is ln concentration versus time. R 0.99998. You don't have to put that, but it sure is good form. Okay. What is the value of the rate constant? K equals the slope of the best fit line. That's why I needed this back on my screen. Make sure you pick up the correct slope. Doesn't do you any good to report the wrong slope. It won't be this k. So that k equals the absolute value of the slope, which is equal to, sitting right here on my screen, forget the negative sign, that's what absolute value means, 9.9, I got to call it 1 because that 5, times 10 to the negative 1, 2, 3. And what are its units? This is first order. So my one finger is up since it's first order overall. Now my one finger goes down. And so I don't have any molarities. I just have the time unit, which is seconds. So seconds to the -1, or per seconds if you prefer. Okay, that one, I gotta say, it was kind of lame there. Should have had me do it this way. This one's better. What is the order of this reaction? That means do your graph thing. Do them all. Okay, that's a lot to type in. So pause me. Go ahead, pause me. Start typing. Seconds plus clear your lists. All right, start typing. I've messed up if you're watching me. Second plus group. Oh, phooey, that was one we just did, so it must be integrated 3. So, I thought I had these grouped right. I just can't remember which one I did. Ungroup. If this doesn't work, I'm going to have to resort to typing. And you're not going to want to watch me do that. You're going to want to fast forward through all of that. Please be the right set. Oh, there, finally. Third time was a charm. Okay, so if I arrow down, go back over here and arrow down, just to make sure I got that last data point in there. I do. There. Okay, so got them all. Sorry about that. So hopefully you fast forwarded through all that mess, where it took me 3 tries to ungroup stuff. All right. That took a little bit of typing. I promise an AP problem won't have more than 4 or 5-ish data points, so it wouldn't take you near that long to type all that mess out. So let's do our thing. And our thing is to realize that this is L1. And if you didn't do it that way, that's okay. Just label it so you know what you did. I wouldn't move them around. I'd just go with what you did. If you forgot to do it that way, lesson learned. This is L2. I want an L3 and I want an L4. L3 will be the natural log of L2. And L4 will equal the reciprocal of L2. So tippy top must be on tippy top. Ln of everything in L2, please. Reciprocal of everything in L2, please. All right, now let's run our regressions. Stat, calc, 4, enter. Didn't mean to do it that way. I took a shortcut, sorry. Calc, 4, second, 1, comma, second, 2, comma, alpha, trace, y equals. This just makes running the pattern faster. So I'm trying to beat a 0.9. Let's see if we can do it. Second enter gets my command back. Go back and type over L2 with L3. 0.97 beats 0.90, so we're on to something. Second enter gets that one back. And let's see if we can beat 0.97. That's our goal. Second 4. Oh, we have a winner. Okay, so this was our winner because we had 0.94, 0.90, 0.94, 0.9999. So that was the best fit, and that is L1, L4, which translates into reciprocal concentration on the y-axis and time on the x-axis, but more importantly, 0, 1, 2 at second order. So what is the order of this reaction, and explain? Second order. Since the graph of reciprocal concentration, concentration of C4H6 to the -1, or you could do 1 over it if you like that better. It's up to you. Versus time. It's always y versus x is linear. Sketch your graph as part of your explanation. So I need to go set up L1, L4, but you know what it's going to look like, right? If you don't, then it's worth graphing. It's the only one with a positive slope. Zoom 9. Stop that. It's beautiful. Do not go through the origin. Notice yours on the screen does not go through the origin. Write the rate law expression. Rate equals K, concentration, C4H6, my only reactant. And what exponent do I put on it? 0, 1, or 2? If it was L1, L4, that's the highest exponent, which is 2. Then it agrees with second order anyway. What is the value of the rate constant? You had to know that was coming. K equals the slope. If I quit my graph and get that data back, there it is. That's the command to get it back. My slope is, and remember K's are always positive. In this case it is positive, but even if it isn't, remember that K is always, always, always a positive number. But my A is 0.0612, and I'm just going to leave it like that. 0.0612 is 3 sig figs. Is that enough sig figs? That's plenty. Okay, now what unit? This is second order. Overall, 2 fingers are up. Drop 1 down. That means there's a molarity down here as well as the time unit of second. What is the half-life of this reaction under the conditions of this experiment? So what are we going to do? How are we going to get that? Well, it's pretty easy if you actually look back up here. What did we start with? We started with 0.01. Did we get lucky enough for there to be a 0.005? Oh, no, we weren't that lucky, but you know what? We can easily do that. All we have to do is look at this graph again. All right, see it? Think about what it is. It is the reciprocal of the concentration that we seek. Oh, no, we know what that concentration is. So we know that if we have 1 over C4H6 at T1/2, that would be equal to the reciprocal of your initial concentration, 0.01, cut in half. Okay, so is that an x value or a y value? Well, that's why they had you sketch it. It's a y value. So come over here to y equals. Make yourself a line of the reciprocal of 0.005. Why 0.005? One more time. Because 0.01 was our starting amount. When half of that is gone, whatever the time is that has elapsed with that is going to be my half-life. So if I find that intersection and get the x value, then I'll have my half-life. Second trace, intersection, enter. And I'm just hitting enter until the word intersection appears on my screen. There it is, 200. T1 half equals the reciprocal of this, time at which. Okay, so T1 half is 200 seconds. Now let's go back up here and make sure that makes sense. So they didn't put a .005. It would have fit sandwiched in right there. And that would have been not 200 seconds. Something is wrong, dadgummit. No, it'd be okay. It'd be okay, because 200 would go right in there. Almost talked myself out of that. So 200 seconds. So did we have a .025? No, but we got close to that. So, yep. I think we're good. If I did that right, .01, .005. I did .005. Did I actually type it that way? Yeah, I did. Okay, we're good. So 200 seconds. Almost talked myself out of that. Okay, so we're going to look at exploring these same techniques with the beginnings of some AP problems. And now, mainly because I want to lower your blood pressure, because there was a lot of data in that last problem. And you need to realize that these aren't going to be so long. So look at that data table. Look at that data table. Oh, look, they gave me graphs. Oh, that one's got a little bit more data. But at this point, it's easier to just look at this and try to figure this out. Okay. Interesting. Not a concentration. But you know what? We can measure just about anything. We can measure color changes with absorbance. We can measure changes in pressures. And since everything in this reaction is a gas, this one does changes in pressure. So second plus for enter. You're welcome to skip these if you know how to do this already. So stat, edit. What always goes in L1? Always, always? That would be time. Did I type right? 600, 1200, 2400, 3600? Good job. 348. So we're just using pressure as a concentration unit. It's perfectly legal. Just got to have some measurable quantity that changes with time. Did I get all that in right? 348, 247, 185, 105, 58. Good job. Okay, so what goes here? Because that is my L1. This is my L2. What is L3 and what is L4? This is Ln of L2, and this is the reciprocal of L2. It's what you define those columns as. So Ln of everything in L2, reciprocal of everything in L2. And there we go. So now we run those regressions. And you know what? Since we already have our calculator set up, we could cheat, but I think it's good for you one more time to set this up from scratch. Stat, calc, item 4, L1, so phooey, I missed. L1, comma, L2, comma, alpha, trace, Y1. Missed a comma. Dang it. Where's the insert? Right there. Comma. Much better. 0.96. Can we beat it? Second enter. Replace L2 with L3. Oh, 0.999. Trying to beat 3 of a kind. Trying to beat 3 of a kind. Ooh, fell back to just 1.9. So second enter. Second enter. You want to run it one more time so the proper equation is sitting in your Y1 should you need to calculate with it. So what did we just determine? We just determined L1, L3 was the best. That's the natural log function, and that means it is 0, 1, 2, first order. So first order, since graph of L1, oh, I don't even want to do it that way, of Ln Ln of pressure, I don't need concentration, Ln of PA versus time was linear. You know the K value, it's sitting on your screen. K equals 4.92 times 10 to the minus 4. What units would it have? Well, if it's first order, there's only one pressure in this case in the denominator if it were, but it's first order. So you just put up one finger, drop one down. All we have for first order is seconds. All right, and then we could play games. We could, now that we have this graph in here, we can zoom 9 it, we can zoom out, we can find stuff. So let's try zoom 9. Got to set up my graph properly. It's trying to do weird things because I goofed up and didn't set up my graph. See, it's still thinking, and mine's slower than yours probably because it's virtual. Okay, so on twice gets you out of a mess sometimes, so that was what I just hit. All right, so I should have set up my graph. Second y equals, what was it? L1, L3 is the best combo, and it was trying to graph L1, L4, so no wonder it was confused with that equation. Second 3, zoom 9, I know. Okay, that's more like it. So, if I know that I want to find 2,000 seconds, let's say, what is the concentration at 2,000 seconds? So then I go second trace, and I know the x value. So when x equals 2,000, because that's a time value, it just flat out tells me what the y is. Y equals 4.84. But when you try to put that in the table, that's a pressure, and it doesn't make sense, right? Why doesn't it make sense? Because this is the natural log of it. So, but remember it stores it as y. So second quit, let's undo that natural log by going second ln, and then alpha y. And 126.8, we'll call 127, makes a lot more sense as a matching data point. So this was the ln of PA, and I just had to undo the natural log to get 127. That looks like a decimal point, but it's really 127. That's better. All right, and then I can do vice versa. What about when this is 25? So I can go y equals and make myself an ln of the pressure. Don't forget the function that you're using. It's ln of the pressure. So ln of 25 millimeters of mercury. Graph it. If you can see the intersection, it can calculate it. If you can't see the intersection, then you need to zoom out. So zoom, command is 3. Nothing happens until you hit enter. Now I'm hoping to see an intersection, otherwise I zoom out again. An intersection is a thing of beauty. Second trace. Intersection is item 5. Just keep hitting enter until you see the word intersection in the bottom left corner of your screen. There we go. So x equals 5,304 seconds. 5,304 seconds. Yes, that makes sense. Okay, so that was the point. Now, there's a real essay question that goes with this, and we'll do that. But right now, I'm just trying to solidify this skill for you. Now, this one's interesting because, yeah, we're in trouble. We only have 2 matching data points. I've got molarity and time for only 2 things. So everything's going to come out a straight line if I do that. So that's a bad plan. I really need 3 data points. I'm missing a question mark there and a question mark there. The easier question mark to fill in is that molarity. And I don't know if you've done a Beer's Law equation just yet or lab just yet, but you should soon do one. You may have done one in first year. But absorbance, this is Beer's Law. A for absorbance, which I have, it's 0.6 for this first data point, is equal to A, B, C. All right, so when I read through this prompt, I get what some of this is. C is the concentration. Okay, that's what I seek. That's molarity. So I'm going to rearrange and say to solve for C, I'm going to take the absorbance and I'm going to divide it by A and B, where the A, the little baby A, is the absorptivity constant, which it tells me has a molar absorptivity constant of 5 times 10 to the minus 3 centimeters. Oops. Centimeters molarity in the denominator. Both are minus 1 on the units. and a path length in centimeters of 1 centimeter. Okay, and the absorbance is sitting there in the table of 0.600, and it's naked. Relish the naked number. So I can actually calculate what the concentration is, and it's going to come out in molarity because I've got a 1 over a molarity in the denominator, and so when that flips up to the numerator, it's going to be an ordinary molarity, which is a good thing if I want concentration and molarity, huh? So 0.6 divided by, open a paren, 5 second EE minus 3. Do I need to multiply it by 1? I don't think so. And we come out with 120. That's not right. Something's wrong. I got something wrong. Phooey. Phooey, phooey. What do I have wrong? Because there's no way. I'm just looking at that going, there's no way. Good question. What's wrong? 0.6 divided by 5 times 10 to the 3. I put minus 3. Ah, well, that'll make a big difference, won't it? It's really nice if you copy the numbers correctly into the problem. That's a 3. So let's try that again. Go back up and grab it. Arrow over and get rid of that minus. Delete. I bet it comes out much more logical now. There we go. 1.2 times 10 to the minus 4. So that would be 0.12 times 10 to the minus 5. Nope, 12 times 10 to the minus 5. Can't do that right either. That makes more sense, right? Because it should be decreasing as it's reacting as time goes by. 12, 4, 3, 1.5. Yes. All right, so I needed that before I could even start my graphing exercise. So I'm going to clear that out. Second plus, clear all my lists. And let's put in time in L1 and molarity in L2. I could do it with absorbance, which may actually be safer, but I just went through the trouble of finding that molarity. But I'll go ahead and do it with absorbance. I did have these 3 data points to start with. So you can see that this works with absorbance as well as it does with molarity. So what have I got going on? 0, 35. So why did I hit 6? I don't know. Bad aim. And 44.2. Got it. Those are times. And then 0.6, 0.2, 0.150. All right, then what would this be? This would be natural log of everything in L2. This would be reciprocal of everything in L2. So second, quit. Clear my screen just for fun. Because I've been doing so many of these, I'm going to cheat. Go up far enough, I should be able to find it. On second thought, it may have been faster just to do it. Just going to grab one and fix it. Okay, so let's start with L1, L2. What happened? Oh, it didn't like that in front, huh? Delete. Delete. Now I bet it'll run it. There we go. That's L1, L2, I think. 0.995 is what I'm trying to beat. Second 3. 0.995 is what I'm trying to beat. Oh, beat it. Okay, so far L1, L3 is in the lead. One more. Let's go get L4. Second 4, enter. 0.99. Okay, L1, L3 is our winner. And if you think about what that is first order, because they go 0, 1, 2, L1, L2, L1, L3, L1, L4, 0, 1, 2. This is first order. So, therefore, first order, and K is equal to the slope of the proper set on my screen right there, L1, L3. Slope is, K rather, is the slope 0.511. And it's first order, so that would just be by the time unit, which is minutes. Okay, so that's kind of the point. Forgive the Beer's Law moment. It didn't hurt you to do it, but I was able to fill that in if I wanted to do the similarity. You're still going to come out with a K that's really close. If you want to test it, no, it won't be exact, but it's going to be on the order of 0.5. All right, so guess what they wanted you to do on this one? They gave you the graphs. How kind. They wanted you to realize that this would have been 0 order, and this would have been first order. And this one is linear. So indeed it is first order. And that if I needed to calculate the slope the old-fashioned way, with rise over run, I had enough numbers and enough data to do that. Personally, if they gave you data, I would have chunked that into the calculator and let the calculator calculate the slope for you, because you're less likely to make a mistake. But it's certainly feasible that you could do it the old-fashioned way, rise over run, where the absolute value of that slope is going to be equal to your K. And because it's first order, K is going to carry a time unit only. And then there's this set to practice. So let's go ahead and do it because it's our last one. We'll finish it off. I doubt many of you are still listening because I bet you got this concept a long time ago. So I want to go second plus for enter stat. L1, at least it was kind. L2. Got all those in right? Type carefully. See, if I were talented, I would like tell you a joke in all that silence. All right, so what are we going to do next? We're going to make the natural log of everything in L2, which were my concentrations in molarity, and we're going to make the reciprocals of everything in L2. Voila. So what are we going to do? We're going to determine the order. We're going to find the value of K, and I can extrapolate and interpolate based on all of that information if I wish. So because it's our last one, we'll do all of that. We took all that time to type this stuff in. We might as well get some use out of it. So, one more time. Stat, calc, for second 1 to get L1, comma, second 2 to get L2, comma, alpha, trace, y vars. If you're doing it the old-fashioned way, it's vars, y vars, enter, enter, enter. Okay, so enter. I'm trying to beat 0.96. Focus right here. I'm trying to beat 0.965. So 0.96 is what I'm trying to beat. Second enter. Swap out my L2 for the L3 that we had just created. 0.99. Okay, 0.99 is in the lead. Back to 0.96. So we have a winner. And it was L1, L3. So get that data back on your screen and think about what L3 was. L3 was Ln of L2, and L4 was reciprocal. I shouldn't have put the line there, huh? Of everything in L2, or your concentrations. Okay, so what does it mean? If L1, L2 would come out best, that would be 0 order. But L1, L3 came out best, so it's first order. If L1, L4 would come out best, it would have been second order. So first order, rate equals K, concentration, X to the 1. Don't have to put the 1, but I'm doing it for emphasis. Rate equals, I've got that data sitting on my screen, so I'm looking at A, and it's 1.98 times 10 to the negative 12. Per minute times the concentration of X. All right, so at what time is concentration of X equal to 0.300 molar? We'll do that first. So I need to go set up the bright graph. And you have to hang on to your head, or you have to in your head, not on your head. Hang on to your head's also a good plan. But you got to hang on to what's in your head, that it's L1, L3 that I need to set up. So I'm happy that this is my best regression. That is what's sitting in my y equals right now. But I need to go set up my stat plot. It needs to be L1, L3. I got lucky on that. And I zoom 9 it, because what I am about to calculate is right here in my data table. 0.00, oh, not 0.00. I needed to make it 0.00. Whoa, what just happened? Did you see that move? That wasn't supposed to happen. Okay, there we go. 0.003 molar. All right, so I really do want it to be right there, 0.0030 molar. So it ought to come out between 20 and 30 seconds. So I know y. That means I have to go to y equals and put in the y that way. It was trying to deal with what I hadn't cleaned out of here. Okay, so what do I need? I need ln of 0.003, y ln, because this is the best fit. It was L1, L3. Missed the 3. That would be bad. Graph. If I see the intersection, I'm golden. There it is. I don't have to zoom out. Yippee skippy. Saves me some time. So second trace. Item 5 is intersection. Hit enter until you see the word intersection. There we go. So the concentration of X is 0.003 when time is equal to 38.7 seconds. Oh, so it would have been right here. I wrote it in the wrong spot. I misspoke earlier then. It should be between 30 and 50 seconds, which 38.7 is really in between 30 and 50 seconds, and that makes sense. All right, so now let's do another one. At what is the concentration when time, or at, let's do at 115 seconds. So I know X, right? That's an X value. So I would go to my graph. I can ignore that line for now and go second trace and tell it 115. If I get an error message, I have to zoom out. So go to, zoom out, enter to make it really zoom out. There you go. If your picture doesn't change, you just need to hit enter. I'm annoyed by that intersection, but it's not a big deal. So now I go second trace again to get the value thing where I can tell it what X equals. X equals 115. It will give me Y, which is not my concentration because that negative sign's a big old giant clue that nuh-uh, no way, Jose. 3,2, blah, 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 but it's stored as Y, thankfully. So second quit. This is a natural log function. So second ln to undo it, and alpha and y resides above the number 1 to post that negative 7.32 blah 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 in, and I come out with 115 0.12366, almost evil, huh? 3. And that makes perfect sense in the table. So hopefully you did not stay with me till the bitter end. We've already done that part. I just want to finish up with one more concept because of the lab. If you're doing the lab that NIMSY has written for the teachers to use, then it's a crystal violet lab. It's a really pretty purple stuff. You're going to mix it with sodium hydroxide, and there's this little thing that we call swamping, which means when you do that crystal violet lab, 2.5 times 10 to the negative 5 molar is its concentration, whereas the concentration of NaOH, which we really only care about the hydroxide ion because it's net ionic reaction going on here, is going to be 10 to the minus 1 molar. That's a factor of 10 to the 4th difference, which is 10,000. So the hydroxide is 10,000 times more concentrated than that crystal violet. So we are swamping the concentration of the crystal violet, which is essentially holding the concentration of the hydroxide constant. For all intents and purposes, it does not vary from the 1 times 10 to the minus 1 molar. So when we do this, we're really calculating a pseudo rate law. I just want to make that point before you actually go off and to do that lab. All right, that's just a recap of all those equations, and this is the next part that we will do in the next recording. Thank you so much if you stayed all the way to the bitter end, but I'm hoping that you really got the hang of this by now. Next time.